Welcome to With a Deep Dive.
Yeah.
Today we're doing something a little different. We're taking a stack of sources often reserved for very specific purposes, think job interviews,
Right.
and turning them into a rapid-fire shortcut for you to become incredibly well-informed about a crucial, yet often overlooked, aspect of technology. Manual software testing. Our primary source is 150 manual testing interview questions and answers for 2025. Now, even if you're not, prepping for a software testing role specifically, understanding how software gets from just an idea to a reliable product in your hands is, well, it's invaluable.
Absolutely.
Our mission today is to pull out the most important insights, give you those aha moments, and make this topic really engaging by showing you why it matters to any software you rely on.
Exactly. It's a field that's rich with fundamental principles that actually extend far beyond just the testing department itself. We'll unpack the core concepts, look at the different methods used to ensure quality, and discuss why these practices are absolutely essential for the stability and usability of, well, pretty much any software you interact with daily.
Okay, let's unpack this then. Our source immediately dives into some foundational distinctions that I think often get confused. Most of us have probably heard of the software development lifecycle, right? The SDLC. But our source highlights an equally critical counterpart, the STLC, the software testing lifecycle. What's often misunderstood about how these two interact, and why is that relationship so crucial for a project's success?
That's a great starting point. The SDLC, it really deals with the creation and coding of software, guiding it from concept to deployment.
Yeah.
The STLC, on the other hand, is entirely focused on its validation and verification. It's really a parallel process, ensuring that what was built works and works correctly.
Parallel. That's key.
Yeah, exactly. If you treat STLC as just an afterthought, something separate from SDLC, you risk finding major issues way too late in the game. And that becomes incredibly expensive to fix.
Okay, so if STLC is about validation and verification, how do those two terms, verification and validation, actually play out differently in practice? It sounds a bit like subtle wordplay, but I imagine there's an important distinction there.
There absolutely is. A big one, actually. Think of it this way. Verification evaluates the software during the development phase. It checks if it satisfies the specified requirements and design.
Right.
It's basically asking, are we building the product right, according to the plan?
Got it. Building it right.
Validation, conversely, evaluates the software after development is done, checking if it meets the customer's actual needs and expectations. That's asking, are we building the right product?
Okay. So one checks against the blueprint, the specs, and the other checks against what the user actually needs or wants.
Precisely. Building it right versus building the right thing.
That distinction is key. Okay, now let's get into the two major testing approaches our source brings up: black box and white box testing. Beyond just the basic definitions, what kind of insights do they offer, and when would a team typically choose one over the other?
Right. So fundamentally, black box testing checks software functionality without knowing its internal code structure at all.
Okay.
It's like testing a sealed black box. You only care about the inputs you provide and the outputs you get back. This is often the first type of testing applied because it mirrors how an actual user interacts with the software.
That makes sense.
Common techniques here include equivalence partitioning, boundary value analysis, and cause-effect graphing, which helps visualize the logical relationships between inputs and outputs to identify effective test cases.
Equivalence partitioning sounds interesting for, efficiency. How does it actually reduce testing time? And how does it differ from boundary value analysis? Our source mentioned that, too, with a printer cartridge example.
Yeah, good question. Equivalence partitioning works by dividing input data into partitions or groups of equivalent data.
Okay.
So, for instance, if any score from 90 to 100 gets an A grade, you'd pick just one score in that range, maybe 95, and one outside, like 89. You don't need to test 90, 91, 92, all the way up.
Right. You assume they all behave the same.
Exactly. Boundary value analysis, though, it focuses specifically on the edges or boundaries of those ranges because that's where errors most frequently pop up.
The transition points.
Precisely. For that printer cartridge example, minimum order of 5, 20% discount. For 100 or more, you test values like 4, 5, 99, and 100.
Yeah.
These are the critical points where the logic changes. It's about being smart with your tests, not just exhaustive.
Okay, so strategic poking at the edges. Got it. Now, what about white box?
White box testing, conversely, dives deep into the internal structure of the code itself.
Inside the box now.
Yeah, exactly. Analyzing things like code coverage. Did you run every line? Branch coverage, did you test every if statement outcome? Path coverage, did you follow all possible routes through the code? It's also known as code-based or structural testing.
Hmm.
Its types include statement coverage, making sure every line of code executes, and decision coverage, which checks that every branch point, every decision in the code has been exercised both ways, like true and false.
Okay.
This approach verifies things like potential security holes, incomplete or broken paths in the logic, the flow of the structure itself, ensuring expected outputs for specific code paths, checking conditional loops, and generally ensuring line-by-line code quality. Sometimes aiming for, 100% coverage, though that's often debated.
So it's really about dissecting the internal mechanics.
Yeah.
When would a team prioritize this over black box? What kind of, unique bugs does it excel at finding?
Well, white box testing is critical when you need to understand why something is failing internally or when security and performance are absolutely paramount. It's often done by the developers themselves or by specialized white box testers. It excels at finding logical errors, maybe dead code that's never executed, or security vulnerabilities that might not be immediately obvious just from using the software externally.
Right.
For instance, a function might seem to produce the correct output in most cases, but white box testing could reveal, say, a really inefficient loop that slows performance dramatically only under very specific rare conditions. Black box might miss that.
That's fascinating. There really are completely different lenses into software quality.
Yeah.
You also mentioned static and dynamic testing earlier. How do they really complement each other? What distinct benefits does each offer in finding defects?
They're highly complementary, yeah. Static testing is all about analyzing the code and the documentation without executing the software.
So not running it?
Nope. Think of it like a thorough code review, or using automated tools to scan the source code for common errors, style violations, potential bugs like uninitialized variables, or even security flaws in the code structure itself. It can find these things very early, before the code is even runnable sometimes.
That sounds efficient. Catching things early.
Definitely. Dynamic testing, however, requires executable code. You actually run the software, provide inputs, and observe the outputs and behavior. This is where you find runtime errors, performance bottlenecks, memory leaks, or issues with the user experience that static analysis simply can't detect because it's not seeing the program in action.
Right.
Our source highlights that together they cast a much wider net for finding different types of defects. You really need both.
Okay, that makes perfect sense. Now let's trace the journey of software through this gauntlet of quality checks. Our source outlined 4 distinct test levels. How do these levels build upon each other, guiding a product from just isolated bits of code to something that's actually user-ready?
Yeah, they progress logically, building on each other. We start with unit testing, sometimes called component, program, or module testing. That focuses on the smallest individual pieces of code, like a single function or class.
In building blocks.
Exactly. Then comes integration testing, where those units are combined and tested together to make sure they work with each other.
Okay.
After that, you have system testing, which evaluates the entire application as a whole, integrated system.
The big picture.
Right. And finally, there's acceptance testing, which determines if the product actually meets the user's needs and is acceptable for deployment. Each level has a specific scope and objective, systematically building confidence in the software as you go up.
Integration testing sounds like where the rubber really meets the road. Where individual pieces start working together or maybe don't work together. What are some of the unexpected complexities or common issues that pop up at this stage?
Oh, absolutely. This is where individually perfect units might just not play well together at all. You're looking for interface defects, problems with data flow between modules, or issues with how different components communicate.
Right.
And often, not all the components are ready at the same time, right? So we use techniques involving stubs and drivers.
Ah, yes, I saw those mentioned. Stubs and drivers.
Yeah, stubs are basically dummy modules. They're used in a top-down integration approach to simulate a lower-level module that hasn't been built or isn't ready yet, so the higher-level module has something to call.
Okay, like a placeholder.
Exactly. And drivers are used in a bottom-up approach. They simulate a higher-level module that calls the component currently being tested.
Gotcha.
The complexity really comes from ensuring that as you add new pieces into the mix, they don't break the functionality that was already working between the existing integrated parts. It gets tricky.
I can imagine. And after all the pieces are integrated, the whole system comes together. What's the core focus of system testing then, and why is it often called end-to-end testing?
System testing is about finding defects when the application is tested as a complete integrated whole. often in an environment that's set up to mimic the actual production environment as closely as possible.
Okay.
It truly is end-to-end because it validates all the software requirements against the complete system. This includes checking interactions with external interfaces, like other systems it needs to talk to, or databases. You're verifying that the entire thing functions as intended, from clicking a button in the user interface all the way through the processing logic to data storage and retrieval, and back again.
Right, the full journey. So the final checkpoint before a product actually reaches users is UAT, user acceptance testing. How does that fundamentally differ from system testing? And what unique insights do alpha, beta, and pilot testing provide within UAT?
That's a crucial distinction. While system testing verifies the product against its specifications, did we build what we said we'd build? UAT verifies it against the user's actual needs and business requirements. Is it fit for purpose?
Okay. User needs versus specs.
Exactly. It's often done by the actual end users or clients. Now, within UAT, you have different flavors. Alpha testing is usually pre-release and performed by end-user representatives, but at the developer site, often in a more controlled lab environment.
Okay, internal users first.
Sort of, yes. Beta testing is performed by potential customers or actual users at their own locations out in the real world. It's a less controlled setting, usually with a broader audience, to get wider feedback before a full launch.
Right, like a public beta sometimes.
Yeah, it could be. And pilot testing is a very specific type of UAT. It involves a small controlled group of actual users using the product with real data in a live or near-live environment before a full, widespread deployment. The key difference between pilot and beta often involves the use of live data and the specific goal of validating production readiness in a limited scope.
Okay, that clarifies the different flavors of UAT. This whole journey through testing levels, it sounds a lot like the V model our source mentions. Why is this model so highly regarded in software development, especially for emphasizing early testing?
The V model is powerful because it visually represents the relationship between the development phases and the testing phases. It's shaped like a V, right?
Yeah.
To show that for every development phase on the left side, descending down the V, there's a corresponding testing phase on the right side, ascending up the V.
Okay, parallel tracks again.
Exactly. This structure inherently emphasizes early testing by linking specific tests like acceptance tests back to requirements, system tests back to high-level design, integration tests back to detailed design, and unit tests back to code modules right from the beginning.
Mhm.
The main benefit, really the core idea, is that finding defects early during requirements gathering or design is significantly cheaper and easier to fix than finding them late in the process, like after the code is written, or worse, post-release.
Much cheaper, I bet.
No, orders of magnitude cheaper. The V model is driven by that understanding. Waiting to test just racks up costs and increases project risk.
So given this structured approach, does it mean test cases are always written sequentially, along with the development? Our source suggests black box test cases are written first. What's the practical reason for that order?
That's a practical point, yeah. Practically speaking, black box test cases can often be written much earlier in the cycle
Why is that?
because they rely solely on the requirement documents and functional specifications. Those documents are usually available relatively early near the project's outset. You don't need to know anything about the internal code architecture to write black box tests.
Right, you just need the what, not the how.
Precisely.
Yeah.
White box test cases, on the other hand, require a deep understanding of the internal design, the algorithms, the code structure itself, and that information only becomes available much later in the development timeline once coding is well underway or even nearing completion.
Okay.
So writing black box tests first is really about leveraging the information you do have early on to get a head start on test design and preparation. It's about parallel activity again.
Makes sense.
Okay.
Inevitably, even with the best plans and models, flaws will emerge. So let's now dive into the world of defects themselves. What's the fundamental distinction that separates a mere defect from a costly failure?
It's a simple but crucial distinction. A defect is essentially an error, a flaw, a fault in the software code or logic or requirements.
Okay.
When that defect actually reaches the end customer and causes the software to behave incorrectly, crash, or just not meet their needs, then it becomes a failure.
So the impact on the user is the key.
Exactly. If we identify and resolve the defect internally before it ever impacts a user, it remains just a defect. Our source also categorizes defects, which is useful. They mention wrong, where a requirement was implemented but incorrectly.
Okay.
Missing, meaning a required specification wasn't implemented at all, or a customer need simply wasn't met by the software.
Right.
Or even extra, where a feature or requirement was incorporated that wasn't actually asked for by the customer. This can add unnecessary complexity, confusion, or even introduce new risks.
Interesting. Extra can be a defect too. Now, what about those tricky hidden issues? Latent and masked defects. How does knowing about these types change a tester's strategy? Why is distinguishing them important beyond just, academic curiosity?
Oh, these are indeed fascinating and really important for testers to understand. A latent defect exists in the code, it's there, but it hasn't actually caused a failure yet because the specific set of conditions required for it to manifest simply haven't been met during testing or use so far.
Like a hidden time bomb.
Exactly. It's just waiting for the right trigger. A mask defect also exists, but its failure is being hidden or prevented by another defect somewhere else in the system.
How does that work?
Our source gives an example. Imagine some code correctly prevents users from entering negative input values. That's good. But maybe, hidden behind that check, there's an unhandled system exception that would crash the program if a negative number actually managed to get through. The first defect, the lack of the exception handler, is masked by the effective input validation. Ah, okay, so fixing the masking defect could reveal the masked one.
Precisely. Knowing about these forces a tester to think beyond just the immediate obvious failures. They have to consider unusual scenarios, edge cases, complex interactions, and the potential for one issue to obscure another. It means more thorough, more creative, sometimes more devious testing is needed.
That's a powerful distinction, really pushing testers to think proactively. Let's shift to how testers actively find these issues. What is exploratory testing? It sounds less structured, maybe more intuitive. What kind of mindset does it require?
Exploratory testing is indeed less scripted, very hands-on. It's often described as simultaneous test design and execution.
Okay.
Testers don't follow rigidly predefined step-by-step test cases. Instead, they usually start with a test charter. This is a brief document outlining a general scope, maybe some objectives, and the approach for a short, time-boxed testing session, maybe an hour or two.
A mission for the session. Yeah, exactly. The focus is on discovery, learning, and investigation. It requires a really curious, analytical, investigative mindset. The tester is constantly learning about the software as they test it, exploring unexpected paths, questioning assumptions, trying things out.
This is more like detective work.
Very much so. And while test cases aren't formally documented in advance, like in scripted testing, good exploratory testers take detailed notes during their session so they can reliably reproduce any bugs they discover and report them clearly.
Got it. And what about regression testing? That term comes up constantly. It seems to be a really big deal in every development cycle. Why is it so crucial, and when does it typically need to be performed?
Regression testing is absolutely fundamental for maintaining software quality over time, especially as software evolves. It's essentially the repeated testing of an already tested program after any modifications have been made.
Modifications like?
Like a bug fix, adding a new feature, changing configuration, upgrading the operating system or database, basically, any change. The goal is to discover if the changes have introduced any new defects, or if they've unintentionally uncovered or reintroduced old defects that were previously fixed. That's the regression part, making sure things haven't gone backwards.
Right, the dreaded fix broke something else scenario.
Yeah. Our source emphasizes that fixing a bug in one module might unintentionally ripple out and affect other, seemingly unrelated modules. So testing those related modules, or even the whole system, is vital. It should ideally be performed anytime the software or its environment changes.
That sounds like a lot of retesting.
It can be. And that's why regression testing benefits hugely from test automation. Tools that can capture playback user interactions or use output comparators to automatically check if the new outputs match the expected ones can save an immense amount of time and effort here.
Automation is key for regression then. Okay, this raises an important question though. Since testing absolutely everything every single time isn't feasible, how do savvy testers decide what to prioritize? Our source points to risk-based testing.
Yes, risk-based testing is the smart way to handle the impossibility of testing everything. It prioritizes which tests to run based on the level of risk associated with different parts or features of the software.
How is risk determined?
Risk is typically calculated based on two factors: the likelihood of a defect or adverse event occurring in a specific area, and the potential impact it would have if it did occur.
Likelihood and impact.
Okay, so for example, if a particular module handles critical financial transactions and a bug there could lead to significant financial loss or reputational damage, that area would be assigned a very high risk.
Makes sense.
And therefore, it would receive the most intense and thorough testing, both initially and during regression. This ensures that limited testing resources are focused on the most critical and vulnerable areas first. It's about optimizing your testing effort based on potential business damage.
Strategic allocation of effort.
Okay.
Finally, when a defect is found, despite all the planning and testing, what's the first immediate step for a tester? What do they need to do?
The first, most critical steps are usually these three. First, reliably recreate the defect. Make sure you can make it happen again consistently.
Can't fix what you can't find again.
Exactly. Second, capture clear evidence. This is usually a screenshot, maybe a video recording showing the steps, error messages, anything that helps understand the problem.
Proof.
Right. And third, accurately log the defect in the team's bug tracking system. This incident report meets clear steps to reproduce, the expected result, the actual result, severity, priority, environment details, etc.
Okay.
These reports are then used to give clear, actionable feedback to the developers so they can fix it. They also help track the overall quality of the software over time and can even provide insights for improving the development or testing process itself.
Got it. Reproduce, document, report. So what does all this mean for overall project success? Beyond the hands-on defect hunting, our source talks a lot about strategic planning and crucial documentation. What foundational elements make up a comprehensive test plan, for instance? What goes in there?
A test plan is essentially the master blueprint for all the testing activities on a project. It's a formal document describing the scope of testing, what will and won't be tested. It outlines the chosen testing approach or strategy.
Okay.
It details the resources needed, people, hardware, software, tools, and it lays out the schedule for the various testing activities.
So the who, what, when, where, why of testing.
Pretty much. It covers everything from the high-level test objectives, specific features to be tested, features not to be tested, suspension and resumption criteria, entry and exit criteria for each test phase, risk assessment, resource planning, and finally, the test deliverables, the documents the testing team will produce, like test cases, test logs, and summary reports. It's about thinking through the entire testing effort up front.
You mentioned exit criteria there.
Yeah.
What exactly are those, and what could go wrong if a team doesn't clearly define them up front?
Exit criteria define precisely when a particular test level, like unit testing or system testing, or even the entire testing effort for a release, is considered complete. They are predefined conditions that must be met.
Like what kind of conditions?
Oh, things like a certain percentage of planned test cases have been executed and passed. Maybe the number of open high-severity bugs has fallen below a specific threshold. Certain performance goals have been met, or key functional areas have achieved a required level of test coverage.
Okay, objective measures.
Yes, exactly. Without clear, agreed-upon exit criteria, testing can just stop arbitrarily when time runs out, or maybe worse, continue indefinitely in a cycle of just one more fix, wasting time and resources. You risk either releasing software prematurely with too many unknown defects or endlessly polishing something that's already good enough, leading to significant budget and schedule overruns. They provide the definition of done for testing.
That clarity seems vital. Our source also mentions the traceability matrix multiple times, highlighting its importance. What exactly is that document, and what crucial role does it play in ensuring software quality throughout the process?
A traceability matrix is a document, often a spreadsheet, that maps test cases back to specific requirements. It essentially creates a link or a trace between each requirement and the test cases designed to verify it.
So you can see which test covers which requirement.
Precisely. It's typically prepared before test case designing really gets underway or alongside it. Its crucial role is to ensure complete test coverage, to demonstrate that every single requirement defined for the software has at least one test case associated with it, ensuring nothing gets missed.
Avoids gaps.
Yes. It also helps tremendously with managing changes. If a requirement changes later in the project, the traceability matrix instantly shows you exactly which test cases might be impacted and need to be reviewed or updated. It's a critical tool for ensuring requirements are met and for tracking the quality validation process.
Okay, that makes a lot of sense for managing complexity. Now, this whole process is clearly detailed, very structured, but it also relies heavily on the people involved. What are some common pitfalls or risks related to people and environment that can derail testing efforts? And why does our source emphasize the benefit of test independence.
Yeah, the human and environmental factors are huge. Common pitfalls that often lead to project delays or failures include things like just not having enough skilled human resources assigned to testing.
Understaffing.
Right. Or having an improperly set up or unstable testing environment. If the test environment doesn't mirror production accurately, your tests might be invalid. Limited budget for tools or training is another one. And of course, unrealistic time limitations or deadlines squeezing the testing schedule.
The classic constraints.
Exactly. Now, the concept of test independence is vital here. It means having testers who are, to some degree, independent from the team that wrote the code.
Why is that beneficial?
Because unbiased testers, those not directly involved in the development, often bring a different perspective and are statistically more likely to find different types of defects. Our source specifically highlights that developers, despite their deep technical expertise, often have difficulty testing their own work effectively due to a natural lack of objectivity.
They're too close to it.
Yeah, they might make assumptions based on how they know it's supposed to work, or unconsciously avoid areas they're less confident about. Independent testers don't have those biases. They approach it purely from their requirements or user perspective.
Okay, that makes sense. So facing these risks, resources, environment, bias, how can teams effectively mitigate them and ensure a robust testing process? What practical steps can they take?
Well, some are quite straightforward but crucial. Things like conducting a really thorough investigation and review of the specification documents right at the beginning to catch ambiguities or inconsistencies early.
Get clarity up front.
Yes, and having open and frequent discussions with all stakeholders, developers, business analysts, product owners, even end users if possible, to ensure everyone has a shared understanding of the requirements and expectations. Communication is key.
Absolutely.
And sometimes one of the most effective mitigation techniques is surprisingly simple, just walking through the website or application as if you were a real first-time user. Adopting that naive perspective can uncover significant usability issues or confusing workflows that people familiar with the system might overlook.
Put yourself in the user's shoes.
Exactly. Don't underestimate the power of that fresh perspective.
Good point. Our source also talks about more structured ways to catch issues early, mentioning formal reviews or inspections. How do these processes contribute to catching faults before they even become defects embedded in the code, potentially saving a lot of time and money down the line?
Formal reviews are highly structured processes, specifically designed to find faults in documents like requirements, documents, design specifications, test plans, or even the code itself very early in the life cycle.
Okay, a structured examination.
Yes,
Yeah.
very structured. They typically follow specific defined steps. There's planning, then a kickoff meeting to set expectations, individual preparation by the reviewers, the actual review meeting where findings are discussed, rework by the author to fix the identified faults, and finally, a follow-up to ensure the fixes are adequate.
A whole process.
It is. And there's usually a designated moderator who leads the process, ensures objectivity, tracks metrics, and is responsible for the quality of the review itself. These reviews are incredibly important because they are one of the most cost-effective ways to detect and remove faults. Finding a fault in a requirements document is far, far cheaper than finding the resulting bug in the released software.
Catching it on paper versus in code.
Precisely. Our source stresses that the main benefit of designing tests early, which the V model encourages, and using formal reviews, like inspections, is fundamentally about preventing defects from being introduced into the code in the first place, rather than just finding them later through dynamic testing. It shifts quality focus upstream.
Prevention over cure. That's a great summary. Wow, what an incredible deep dive into the whole world of software quality assurance. We've really journeyed through the entire life cycle, haven't we?
We certainly have.
From those foundational distinctions like black box versus white box testing,
Yeah.
understanding verification versus validation, all the way through the progression of testing levels like integration and UAT.
Mm-hmm. And delving into the nuances of defect management, latent versus masked defects, that was interesting.
Yeah, and highlighting the crucial role of strategic planning, risk assessment, and just plain human insight in delivering reliable software.
And we saw how specific techniques like equivalence partitioning and boundary value analysis give testers powerful, efficient ways to design effective tests, and why understanding models like the V model or the real value of risk-based testing is absolutely key to successful software delivery.
Right.
It's clearly a meticulous process, requires a lot of discipline, but as we discussed, it's about much more than just finding bugs.
Exactly. I think you, our listeners, have now got a much more robust understanding of how software gets rigorously examined, poked, prodded, and polished to ensure it actually works as expected and, crucially, meets your needs as a user.
It's really about building confidence in that product. Confidence for the developers, for the business, and most importantly, for the end users.
Precisely. Confidence and trust in the digital tools we rely on every single day. So, considering everything we've unpacked today, here's a final thought. The next time you encounter a software update, or maybe download a new app, how might understanding these testing principles empower you to evaluate its quality? Not just looking at its surface features, but thinking about its underlying reliability, its robustness, its fitness for your purpose.
Judging it on more than just the shiny interface.
Exactly. Something to think about. Stay curious.
City.